Now let's talk about the hard kind of friction, static friction. I have here an ugly block, and I've attached to it a string which is attached to this spring scale which measures force in newtons. And if I pull with this spring scale with a force of 2 newtons, and the block does not move, let me draw a free body diagram of the block. I've got weight, there's no magnets. What touches the block? Well, the string. It pulls. I got the table pushing. Whenever one thing pushes on another, there will always be a normal force. In this case, there will also be a friction force. And I drew the friction force really long because it did not move at all. It really did not move. Oh, wait. Doesn't bother anybody? What's this diagram gonna do? Yeah, it's gonna have this block screaming towards the open door. That's just spooky. That's not what happens. Okay, that friction force has to be exactly 2 newtons. If the acceleration's 0, that diagram has to scream balance by Newton's second law. Okay, now if I pull instead with 4 newtons, and it doesn't go anywhere, and indeed it doesn't, well, the friction's 4. If I pull with 16 and it doesn't go anywhere, the friction's 16. Now, that's what makes this static friction so hard. It can be 2, it could be 4, it could be 16. I imagine I could have made it 12.3. It could be anything. Anything up to a point. At some point, I'm going to pull so hard that this thing is going to break free. Now let's say that happens at 16.01 newtons. All of a sudden it takes off to the left. It moves. Now if I look at that free body diagram, what do I know about that friction force? What can you tell me about that friction force? It's got to be less than 16. Right? Because my diagram is screaming to the left to give me that acceleration. What else do you know about that friction force? What flavor is it now? It's kinetic. Now I can hear the scraping going on. So it's exactly that big. Plug into that formula and that'll tell you exactly how big it is. Okay? So, here's the bottom line. Static friction adjust to the demands. If I push with 100 newtons, if I push with 100 newtons and it doesn't go anywhere, the friction's 100 newtons. Okay? It adjusts to the demands. What that means is that I don't have a formula for static friction. I don't have a handy-duty little plug and chug thing. Now, you didn't seem to have any trouble figuring out how big the friction was, even without a formula. How big is the friction right now? 6 newtons. How do you know? What did you use? By what law? By second law. You got to finish your sentence. By second law with 0 acceleration. When you're calculating a static friction force, 99% of the time, you use Newton's second law. Newton's second law. Okay? Now, it turns out that there's that 1% of the time. And that 1% of the time is right when you're on the verge of breaking free. And you'll recognize when you're at one of those 1% moments, because the wording in the problem will say, what's the hardest you could pull? Or what's the biggest you could accelerate this before it breaks free? Now, it turns out that maximum amount of friction depends on 2 things. And it shouldn't surprise you that those 2 things are how rough the surfaces are and how tightly they're pressed together. Okay? Now, here's the problem. Here's what makes this so challenging. Is that when you get to that exam, some of you are very, very dependent upon the equation page. You get to the exam and you turn off your brain and you just start plugging into formulas. Now on the front page of your exam there will be these formulas. And where people make the biggest mistakes on that next exam is by using that formula. That formula only applies in 1% of the problems. In 99% of the problems, you're nowhere close to this maximum value of the static friction. This is not a formula for static friction. It is not a formula for static friction. It is not a formula for static friction. Are you listening? It is a formula for the maximum value of static friction. The maximum value. Okay?